Galaxies are gravitationally bound systems of stars, gas, dust, and dark matter. Their shapes range from orderly spirals to irregular clouds, and this diversity reflects the complex history of cosmic structure evolution over billions of years. Spiral galaxies make up about 60% of all observed galaxies in the nearby universe. Their characteristic structure includes a bright central core surrounded by a flat disk with winding arms. Our own Milky Way galaxy belongs to this type. The diameter of a typical spiral galaxy ranges from 30,000 to 100,000 light-years, although larger examples also exist. Spiral arms are not solid structures. The stars within a galaxy orbit around its center at different speeds, depending on their distance from the core. With such differential rotation, any rigid structure would smear out within just a few revolutions, a process taking only a few 100 million years. Yet spiral arms persist for billions of years. The density wave theory, proposed in the mid-20th century, explains this apparent contradiction. According to this model, spiral arms are not composed of the same stars, but rather regions of higher density through which stars pass as they orbit the galactic center. Imagine a traffic jam on a highway. Cars move through it, but the jam itself remains roughly in place, or moves more slowly than the cars. In these high-density regions, gas is compressed, triggering the formation of new stars. Young, hot stars shine brightly in blue and ultraviolet light, making spiral arms especially prominent. These massive stars live relatively short lives, only a few million years, so they don't travel far from their birthplaces. This explains why spiral arms appear so bright and blue. Not all spiral galaxies are the same. There are regular spiral galaxies and barred spiral galaxies. In barred spirals, an elongated structure passes through the center, with spiral arms extending from the ends of the bar. About 2/3 of all spiral galaxies, including the Milky Way, have bars. Simulations show that bars can naturally form due to gravitational disturbances in the galactic disk, and may periodically appear and disappear throughout a galaxy's lifetime. Elliptical galaxies differ greatly from spirals. Their shapes range from nearly spherical to elongated, resembling a rugby ball. They lack a distinct disk structure, and their stars move along chaotic orbits rather than rotating in a single plane. Elliptical galaxies contain very little cold gas or dust, so new stars rarely form in them. They are mostly populated by old red stars. The sizes of elliptical galaxies vary dramatically. Dwarf ellipticals may contain only a few million stars, while giant ellipticals can host trillions of stars and span hundreds of thousands of light-years across. The most massive galaxies in the universe are almost always giant ellipticals, located at the centers of large galaxy clusters. The formation of elliptical galaxies is linked to the merging of other galaxies. Computer simulations show that the collision of two spiral galaxies can lead to the creation of an elliptical one. During such a merger, gas is compressed, triggering an intense burst of star formation that quickly depletes the material needed for future stars. Gravitational interactions disrupt the orderly rotation of the disks, transforming them into a system of chaotic stellar orbits. However, not all elliptical galaxies necessarily formed through mergers. Some may have formed directly from primordial gas during the early stages of the universe's existence. In the first few billion years after the Big Bang, conditions were very different. Galaxies formed more rapidly, and collisions occurred more frequently due to the smaller distances between emerging structures. Irregular galaxies have no clearly defined structure. They appear chaotic, lacking the symmetry characteristic of spiral and elliptical galaxies. This category includes various types of galaxies, united by the absence of a regular shape. Some irregular galaxies are rich in gas and show active star formation, while others are the result of gravitational interactions between galaxies. The Magellanic Clouds, visible in the southern hemisphere of Earth, are examples of irregular galaxies. The Large Magellanic Cloud lies about 160,000 light-years from Earth and contains around 10 billion stars. The Small Magellanic Cloud is located even farther away, at about 200,000 light-years. Both are satellites of the Milky Way and are slowly being absorbed by our galaxy. Tidal interactions play an important role in the formation of irregular galaxies. The gravitational attraction between closely passing galaxies pulls out long streams of stars and gas, distorting their original structure. The famous Antennae Galaxy system is a pair of colliding galaxies with enormous tidal tails, stretching for hundreds of thousands of light-years. The evolution and shape of galaxies are closely linked to their environment. Galaxies in dense clusters are more likely to interact with neighbors, leading to mergers and transformations. Elliptical galaxies dominate in such clusters, while spiral galaxies are more common in less dense regions of the universe. This ratio changes over cosmic time. In the early universe, irregular galaxies were more common than they are today. Supermassive black holes at the centers of galaxies also play a key role in their evolution. Nearly every massive galaxy contains a black hole at its center, with a mass ranging from millions to billions of solar masses. The mass of the central black hole correlates with the mass of the galactic bulge, the central spheroidal component of the galaxy, indicating a close connection between black hole growth and galaxy formation. Active galactic nuclei, AGN, where supermassive black holes accrete surrounding material, emit enormous amounts of energy. This energy can drive gas out of the galaxy, halting star formation. Such feedback from black holes may explain why the most massive galaxies are elliptical and contain little gas. Their black holes have expelled much of the material needed for star formation. Dark matter makes up most of a galaxy's mass, although it remains invisible. Galaxies are embedded in vast dark matter halos that extend far beyond their visible stars. The distribution of dark matter determines the galaxy's gravitational potential and affects the motion of stars and gas. Variations in dark matter distribution can lead to different galaxy morphologies. Simulations of galaxy formation within the framework of the modern cosmological model show that initial conditions and the subsequent merger history determine a galaxy's final shape. Galaxies that grew mainly through the smooth accretion of gas without major mergers developed spiral structures. Those that experienced significant mergers evolved into elliptical galaxies. Those that have recently undergone strong disturbances may appear irregular. Observing distant galaxies allows astronomers to look into the past, since the light from them travels for billions of years before reaching us. Galaxies in the early universe, seen as they were just 1 to 2 billion years after the Big Bang, appear more compact, irregular, and show more intense star formation. Well-defined spiral structures become common later, about 5 to 6 billion years after the Big Bang. This evolutionary picture aligns with the hierarchical model of structure formation, where small galaxies form first and later merge to create larger systems. In this scenario, Modern massive galaxies are the result of numerous mergers of smaller galaxies throughout cosmic history. The morphology of a galaxy reflects the balance between different processes: gas accretion, star formation, mergers, and feedback effects. Lenticular galaxies, S0 type, represent an intermediate class between spiral and elliptical galaxies. They have a central bulge and a disk like spirals, but lack distinct spiral arms and contain little gas, similar to ellipticals. The origin of lenticular galaxies remains a subject of active research. They may be former spiral galaxies that lost their gas due to interactions within clusters, or they might represent an early stage of evolution preceding the formation of spiral arms. Interaction between a galaxy and the intergalactic medium in clusters can greatly affect its evolution. The pressure of oncoming gas removes cold gas from a moving galaxy, a process called ram pressure stripping. A galaxy deprived of gas can no longer form new stars, leading to the transformation of a spiral galaxy into a lenticular or elliptical one. Galaxies located at the centers of rich clusters often show signs of such interactions. Angular momentum plays a fundamental role in determining a galaxy's shape. A protogalactic cloud of gas with a high angular momentum flattens into a disk during collapse, conserving its rotational motion. Such systems form spiral galaxies. Clouds with lower angular momentum collapse into more spherical configurations, forming elliptical galaxies. Mergers can redistribute or reduce angular momentum, changing the morphology of a system. Stellar populations in different types of galaxies differ not only in age, but also in metallicity. In astronomy, metallicity refers to the abundance of elements heavier than hydrogen and helium. Old stars in elliptical galaxies generally have higher metallicities than stars of the same age in spiral galaxies, indicating distinct histories of chemical evolution. Elliptical galaxies went through an early era of intense star formation, rapidly enriching the interstellar medium with heavy elements. Spiral galaxies, on the other hand, formed stars more gradually, stretching the process of chemical enrichment over billions of years. These differences are reflected in the observable properties of stellar populations and help astronomers reconstruct the histories of galaxies. The rotation of galaxies also reveals fascinating patterns. Spiral galaxies rotate in an orderly fashion, with most stars moving in the same direction within the plane of the disk. The rotation speeds at different distances from the center, known as rotation curves, do not match the distribution of visible matter. Instead of decreasing, they remain roughly constant or even increase at large distances, where few visible stars exist. This discrepancy is one of the key pieces of evidence for the existence of dark matter. The dark matter halo surrounding the galaxy provides the additional mass necessary to explain the observed rotation speeds. Without dark matter, the outer regions of galactic disks would rotate much more slowly. According to Newton's laws of gravity, observations of the rotation curves of thousands of galaxies confirm the presence of large amounts of invisible matter. Elliptical galaxies do not exhibit ordered rotation of the entire system. Instead, stars move along a wide variety of orbits, forming a structure supported more by random motion than by rotation. Velocity dispersion, the spread of stellar velocities, determines the structure of an elliptical galaxy. More massive ellipticals have higher velocity dispersions, reaching hundreds of kilometers per second. Galactic winds, caused by supernova explosions and stellar radiation, can expel gas from a galaxy. This process is especially effective in smaller galaxies with a weaker gravitational potential. The loss of gas halts star formation and can drastically change the galaxy's further evolution. Dwarf galaxies often show evidence of such outflows, with bubbles of hot gas extending beyond the stellar body. Ultra-compact dwarf galaxies represent a mysterious class of objects. They contain tens to hundreds of millions of stars compressed into regions only a few hundred light-years across. Their density is far higher than that of typical dwarf galaxies. The origin of ultra-compact dwarfs is still debated. They may be remnants of larger galaxies stripped of their outer regions through tidal interactions, or a special type of compact stellar system. Tidal dwarf galaxies form from material torn out of interacting galaxies. Tidal forces stretch galaxies, and part of this material can become self-gravitating and form a separate structure. Some observed dwarf galaxies show properties indicating such an origin, including unusual stellar populations and kinematics. Numerical simulations of galaxy interactions and mergers have reached a high level of realism. Modern simulations take into account not only gravity, but also gas dynamics, star formation, feedback from supernovae and black holes, and many other physical processes. These models reproduce many observed properties of galaxies of various types and help test theoretical scenarios of their formation and evolution. Simulation results show that the details of feedback mechanisms are critically important for obtaining realistic galaxies. Without effective feedback, simulations produce galaxies with too many stars and too little gas compared to real observations. Proper modeling of processes regulating star formation, such as gas ejection by stellar radiation and supernova explosions, is essential to reproduce the observed diversity of galaxies. Interaction between a galaxy and its environment manifests in many forms. Galaxies falling into clusters undergo several processes that alter their properties. In addition to ram pressure stripping, there is galaxy harassment, multiple rapid gravitational encounters with neighbors, and tidal interactions with the cluster sheath's overall gravitational potential. These effects accumulate over time, gradually transforming a galaxy. The color of a galaxy correlates with its morphology. Spiral galaxies are typically bluer because of young, hot stars in their spiral arms, while elliptical galaxies appear redder, consisting mostly of old stars. This color morphology correlation is not absolute. There exist red spirals and blue ellipticals, but such objects are relatively rare and represent transitional or unusual evolutionary stages. Red spiral galaxies, deprived of gas and star formation, may represent a stage in the transformation into lenticular galaxies. Blue elliptical galaxies often show signs of recent mergers with gas-rich galaxies, which triggered a new burst of star formation. Studying such unusual objects helps scientists understand the processes that govern the evolution of galaxies. Ultra-diffuse galaxies represent another mysterious class of objects. These galaxies are comparable in size to the Milky Way, but contain 100 times fewer stars, making them extremely diffuse and difficult to detect. Their formation and nature remain poorly understood. Some models suggest that they are galaxies with an exceptionally high dark matter content, while others propose that they are galaxies stripped of their stars as a result of tidal interactions. The fundamental plane of elliptical galaxies describes a correlation between a galaxy's effective radius, its average surface brightness, and its velocity dispersion. all elliptical galaxies lie close to this plane in three-dimensional parameter space, indicating a unifying process in their formation. The fundamental plane is also used to estimate distances to elliptical galaxies and to study their evolution over time. The Tully-Fisher relation for spiral galaxies connects a galaxy's rotation speed with its luminosity. Brighter spiral galaxies rotate faster. This relation also serves as a tool for measuring cosmological distances. The existence of such correlations shows that the properties of galaxies are not random, but are governed by fundamental physical laws. The virial theorem, when applied to galaxies, links the kinetic and potential energy of a system. For a stable, gravitationally bound system, the average kinetic energy equals half the negative potential energy. This theorem allows astronomers to estimate a galaxy's mass based on the observed velocities of its stars or gas. Applying the virial theorem to galaxy clusters provided the first evidence for the presence of unseen matter as early as the 1930s. The stellar arms in spiral galaxies display a great variety of structures. Some galaxies have two well-defined arms, while others possess numerous fragmented ones. The number and nature of the arms depend on several factors, including the galaxy's mass, rotation speed, gas content, and the presence of a bar. The density wave theory successfully explains large spiral arms, but the detailed structure of smaller branches requires consideration of additional processes, such as magnetic fields and local gravitational instabilities. Jellyfish galaxies get their name from the long gaseous tails, resembling jellyfish tentacles. These structures form as a galaxy moves through the dense intracluster medium. The ram pressure of the oncoming gas strips cold gas from the galactic disk, creating elongated streams. Star formation often occurs within these tails, producing chains of young stars trailing behind the galaxy. Ring galaxies exhibit an unusual structure with a bright ring of stars surrounding the center. They form as a result of a direct collision. When one galaxy passes through the center of a disk galaxy, a shock wave propagates outward from the point of impact, compressing gas and triggering a radially expanding wave of star formation. The Cartwheel Galaxy is a well-known example of such a structure. Gravitational lensing allows astronomers to observe distant galaxies that would otherwise be invisible. A massive foreground galaxy or galaxy cluster bends the light of more distant objects, magnifying and distorting their images. Strong lensing produces multiple images, or Einstein rings, while weak lensing causes subtle distortions in the shapes of background galaxies. Statistical analysis of thousands of such galaxies enables astronomers to map the distribution of dark matter. Polar ring galaxies consist of gas and stars rotating in a plane perpendicular to the main body of the galaxy. The origin of these structures is linked to either accretion of external material or a merger with a smaller galaxy whose orbit was nearly perpendicular to the main galaxy's disk. Polar rings provide a unique opportunity to study the three-dimensional distribution of dark matter in galaxies. The rapid advancement of observational technologies continues to expand our understanding of galaxies and the vast, complex universe they inhabit. Space telescopes provide detailed images of galaxies across various ranges of the electromagnetic spectrum. Observations in the infrared penetrate dust, revealing hidden regions of star formation. X-ray observations detect hot gas and active black holes. Radio observations map the distribution of cold gas and magnetic fields. Spectroscopic surveys measure the redshifts of hundreds of thousands of galaxies, charting their three-dimensional distribution in space. These data reveal the large-scale structure of the universe, a cosmic web of filaments and voids. Galaxies are not distributed uniformly, but cluster along filaments surrounding vast, low-density voids. This structure emerged from small initial density fluctuations in the early universe, amplified by gravity over billions of years. A galaxy's position within the large-scale structure affects its evolution. Galaxies in filaments experience moderate environmental influence. Those in nodes, where filaments intersect and clusters form, undergo intense interactions, while galaxies in voids evolve in relative isolation. These environmental differences lead to the observed morphological segregation, where certain galaxy types dominate specific regions. The reionization of the universe, which occurred within the first billion years after the Big Bang, was driven by the radiation of the first stars and galaxies. Before reionization, the universe was filled with neutral hydrogen, opaque to ultraviolet radiation. Ultraviolet photons from the first luminous objects ionized the surrounding gas, creating expanding bubbles of ionized matter. These bubbles eventually overlapped, completing the reionization process. Studying the most distant galaxies helps us understand this critical transition in cosmic history. The first galaxies were smaller and more compact than present-day ones, forming in low-mass dark matter halos. Their metallicity, the abundance of elements heavier than hydrogen and helium, was extremely low, close to primordial composition. The population through stars, the hypothetical first stars, completely devoid of metals, may have been much more massive than modern stars, reaching hundreds of solar masses. The formation of the first supermassive black holes poses a theoretical challenge. Quasars, active galactic nuclei, powered by black holes, with masses of billions of suns, are observed only a few 100 million years after the Big Bang. Growing such massive black holes in such a short time is difficult, even with continuous accretion at the maximum possible rate. Various scenarios have been proposed, including the direct collapse of massive gas clouds into black holes without a preceding stellar phase. Brown dwarfs, objects intermediate between stars and planets, lack sufficient mass to sustain stable hydrogen fusion. Their masses range from 13 to 80 Jupiter masses. They emit faint light from gravitational contraction and residual formation heat, gradually cooling over time. The population of brown dwarfs in galaxies is hard to detect due to their low luminosity, but contributes to the total stellar mass. The metallicity of galactic gas increases over time as successive generations of stars synthesize heavy elements and expel them into the interstellar medium through stellar winds and supernova explosions. A metallicity gradient is observed in spiral galaxy disks, higher metallicity near the center and lower toward the outskirts, reflecting the history of star formation and gas mixing within the galaxy. Star clusters form from a single giant molecular cloud containing stars of similar age and composition. Open clusters located in spiral galaxy disks contain from a few dozen to several thousand stars. They gradually disperse due to gravitational disturbances, with lifetimes ranging from tens to several hundreds of millions of years. Globular clusters are more massive than open clusters, containing tens or even hundreds of thousands of stars, tightly bound by gravity, which grants them lifetimes measured in billions of years. They surround galaxies in a spherical halo and are among the oldest objects in the universe, with ages comparable to that of the cosmos itself. Studying globular clusters provides insights into the early stages of galaxy formation. The number of globular clusters correlates with a galaxy's mass, and their metallicity reflects the chemical composition of the gas present during their formation. Ultraluminous X-ray sources, ULXs, emit in the X-ray range, with luminosities exceeding the Eddington limit for a black hole of several tens of solar masses. Their nature remains debated. They may represent intermediate mass black holes ranging from hundreds to thousands of solar masses, or stellar mass black holes undergoing extreme accretion. Understanding these sources is crucial for studying the formation of supermassive black holes and galactic evolution. Galactic fountains describe the circulation of gas within galaxies. Massive stars and supernovae heat gas to high temperatures, ejecting it from the galactic disk into the halo. As it cools, the gas falls back into the disk, now enriched with heavy elements. This cycle plays a key role in regulating star formation and chemical evolution. The intergalactic medium, IgM, contains a significant fraction of the baryonic matter in the universe. Most of this gas exists in the form of warm and hot ionized plasma, invisible in optical light. Its presence is detected through absorption lines in the light from distant quasars or X-ray emissions from hot gas in galaxy clusters. Studying the IgM is essential to fully understand the baryon cycle of the universe. Cold gas accretion onto galaxies occurs along the filaments of the cosmic web. Gas flows from the intergalactic medium into galaxies, replenishing their star-forming material. This process was especially important in the early universe, but still continues in some galaxies today. Cold streams can penetrate deep into galaxies, bypassing the hot halo and directly feeding the central regions. Hypervelocity stars, ejected from galaxies by gravitational interactions, move at speeds of hundreds or even thousands of kilometers per second. They can be accelerated through encounters with a binary supermassive black hole in a galactic center, or through the breakup of a multiple star system following a supernova explosion. These stars leave their host galaxies and travel through intergalactic space. Intracluster light originates from stars that no longer belong to any particular galaxy, but are scattered throughout the space between galaxies. In galaxy clusters, these stars are stripped from galaxies by tidal interactions. Observations indicate that up to 50% of all stars in some clusters may reside in this intracluster component. Low surface brightness, LSB galaxies, have extremely diffuse distributions of stars, making them difficult to detect against the background sky. They can be as massive as normal galaxies, but their stars are spread over a much larger area. These galaxies are often rich in gas and dark matter, but have low star formation rates. Studying them is important for understanding the complete census of galaxies and the processes regulating star formation efficiency. Superclusters of galaxies represent the largest gravitationally bound structures in the universe, containing dozens or hundreds of galaxy clusters, stretching across hundreds of millions of light years. They form the nodes and filaments of the cosmic web. The local supercluster, to which the Milky Way belongs, is called Laniakea and contains approximately 100,000 galaxies. The Great Attractor is a gravitational anomaly in space, toward which the local group of galaxies, along with many neighboring galaxies, is moving. It lies approximately 200 million light-years away, in the direction of the constellations Hydra, and Centaurus. The Great Attractor is associated with a mass concentration in this region, including the Norma Cluster. Studying the large-scale motions of galaxies helps map the distribution of mass in the universe and understand the dynamics of cosmic structures. Voids in the universe are vast regions with a low density of galaxies, surrounded by filaments and clusters. Their sizes can reach hundreds of millions of light years. Although they are called voids, they are not completely empty. Dwarf galaxies and low-surface brightness galaxies may still populate them. Voids form naturally as part of the gravitational evolution of the large-scale structure of the cosmos. The cosmic web is a foam-like structure representing the distribution of matter in the universe. Galaxies are concentrated in thin walls and filaments surrounding the vast voids. This structure results from the gravitational collapse of small initial density fluctuations that existed in the early universe. The shape and evolution of the cosmic web depend on cosmological parameters, including the density of dark matter and dark energy. Dark energy makes up about 68% of the total energy of the universe and is responsible for the accelerated expansion of space. Its nature remains one of the greatest mysteries of modern physics. Dark energy affects structure formation by suppressing the growth of cosmic structures at later stages in the universe. Evolution. The future fate of the universe depends on the properties of dark energy. Cosmic microwave background radiation, CMB, or relic radiation, is the leftover light from the epoch when the universe became transparent to photons, about 380,000 years after the Big Bang. Small temperature fluctuations in the CMB reflect the initial density perturbations that eventually grew into modern galaxies and large-scale structures. Studying the CMB provides a snapshot of the early universe and crucial information about cosmological parameters. Baryon acoustic oscillations, BAO, are periodic fluctuations in matter density within the large-scale structure of the universe, remnants of sound waves that propagated through the hot plasma before recombination. They imprint a characteristic scale in the distribution of galaxies, which serves as a standard ruler for measuring cosmological distances. These measurements help constrain cosmological model parameters, including the properties of dark energy. Cosmological inflation refers to a period of exponential expansion that occurred during the first fractions of a second after the Big Bang. Inflation explains several observed features of the universe, including its homogeneity, spatial flatness, and the origin of initial density fluctuations. Quantum fluctuations during inflation were stretched to cosmological scales, becoming the seeds for all structures in the universe. Galaxies continue to evolve, and their future depends on cosmological factors. The Milky Way and Andromeda galaxies are moving toward each other and will collide in about 4 billion years, forming a new elliptical galaxy. At that time, the Sun will be nearing the end of its life, and conditions on Earth will have become uninhabitable long before the galactic merger. In the distant future, trillions of years from now, star formation in the universe will cease as gas reservoirs are depleted. Galaxies will consist mainly of dying stars, white dwarfs, neutron stars, and black holes. The accelerated expansion caused by dark energy will eventually tear apart the gravitational bonds between galactic groups and clusters. Isolated galaxies, or their remnants, will drift alone in an ever-expanding cosmic void. The study of galaxies unites many fields of astronomy and physics. Observational astronomy provides data on the properties of galaxies at various distances and epochs. Theoretical models and numerical simulations interpret these data and predict galactic behavior. Astrophysics explains the physical processes within galaxies, while cosmology connects galactic evolution to the overall history of the universe. The diversity of galactic forms reflects a complex interplay of initial conditions, gravitational dynamics, gas physics, star formation, feedback from stars and black holes, and environmental influences. Each galaxy has a unique history, but the same physical laws govern the underlying patterns. Spiral galaxies, with their ordered rotation and ongoing star formation. Elliptical galaxies, with old stellar populations and chaotic dynamics. And irregular galaxies showing signs of recent disturbances. All are products of billions of years of cosmic evolution. Ongoing observational programs continue to expand the sample of studied galaxies, reaching ever more distant epochs and fainter objects. New telescopes with improved sensitivity and resolution allow astronomers to explore the fine structure of galaxies and detect galaxies at the edge of the observable universe. Each new observation adds another piece to the mosaic of our understanding of galactic evolution. Though interstellar dust accounts for only a small fraction of a galaxy's total mass, it plays a crucial role in its evolution. Dust absorbs starlight and re-emits energy in the infrared, altering the observed colors of galaxies. It acts as a catalyst for the formation of molecular hydrogen, which is essential for star formation. Dust also affects gas cooling, a key process for the collapse of molecular clouds. Magnetic fields in galaxies extend across tens of thousands of light years and influence the motion of charged particles and the structure of the interstellar medium. The origin of galactic magnetic fields remains unclear. They may have been amplified from weak initial fields through a dynamo mechanism, where differential rotation and turbulence in conducting gas generate and strengthen magnetic fields. These fields affect star formation, cloud collapse, and the propagation of cosmic rays. Cosmic rays are high-energy particles, mainly protons, that travel through the interstellar medium at speeds close to the speed of light. They are accelerated in shock waves produced by supernovae and other energetic cosmic events. Cosmic rays contribute to the pressure balance of interstellar gas and may influence star formation. Their interactions with the interstellar medium produce gamma-ray emissions observed from galaxies. Molecular clouds are cold, dense regions of interstellar gas, where temperatures drop to just a few tens of kelvins. Under such conditions, hydrogen atoms combine to form molecules. These clouds are the birthplaces of stars. Gravitational collapse within the densest regions of a cloud leads to the formation of protostars. Massive molecular clouds can contain millions of solar masses of gas and give rise to entire stellar clusters. H22 regions, or regions of ionized hydrogen, surround young, hot stars. The ultraviolet radiation from these stars ionizes the surrounding gas, creating glowing nebulae. H2 regions have a characteristic reddish hue due to the recombination emission of hydrogen. Studying these regions allows astronomers to estimate the current rate of star formation in galaxies. Molecular hydrogen, H2, is the main form of gas in the cold regions of galaxies, but it is difficult to detect directly due to the absence of a dipole moment. Instead, astronomers trace molecular gas using carbon monoxide, CO, emission lines. Since CO is the second most abundant molecule after hydrogen, maps of CO emission reveal the distribution of molecular clouds and potential sites of star formation. Neutral atomic hydrogen is observed through its 21 TeC line in the radio spectrum. This line arises from a hyperfine transition between two energy levels of the hydrogen atom as ground state. Observations of this line allow astronomers to map the distribution of gas within galaxies, including the outer disk regions where few stars exist. Maps of neutral hydrogen often extend far beyond the optically visible disk, revealing the full extent of a galaxy's gaseous component. The interactions among various components of the interstellar medium, cold and warm gas, hot ionized gas, magnetic fields, cosmic rays, and radiation, create a complex ecosystem that regulates galactic evolution. Understanding these interactions requires accounting for a wide range of physical processes, operating across scales from individual molecular clouds to entire galaxies. Enrichment of the interstellar medium with heavy elements is an ongoing process as stars evolve. Massive stars end their lives as supernova explosions, ejecting elements synthesized in their cores, and during the explosion itself, intermediate mass stars go through the planetary nebula phase, shedding their outer layers. Binary white dwarf systems can produce type Ia supernovae, which are important sources of iron. All these processes contribute to the chemical evolution of galaxies. Metallicity gradients in spiral galaxy disks show that inner regions enriched faster than outer ones. This may result from higher star formation rates in galactic centers and from radial mixing of gas. Outer regions often accrete less enriched gas from the surrounding environment, diluting metallicity. Detailed chemical evolution modeling helps reconstruct the star formation history and gas flows within galaxies. The interstellar medium, ISM, is inhomogeneous and multi-phase. It consists of cold molecular clouds, cold and warm neutral atomic gas, warm ionized gas, and hot diffuse gas. These phases coexist in approximate pressure equilibrium, but energy input from stellar winds, supernovae, and other sources constantly disturbs this balance, creating a dynamic, turbulent environment. Turbulence in the ISM affects many processes. It prevents the collapse of molecular clouds by providing turbulent pressure opposing gravity. It also promotes mixing of gas, distributing heavy elements, and amplifies magnetic fields via the dynamo mechanism. Sources of turbulence include stellar feedback, rotational shear, and accretion flows of gas. The heating and cooling of interstellar gas determine its thermal structure. Heating occurs through photoionization by starlight, shock waves from supernovae and stellar winds, and interactions with cosmic rays. Cooling happens via radiative emission in spectral lines of atoms and molecules. The balance between heating and cooling defines which gas phases can exist at given densities and pressures. Superbubbles are giant cavities of hot gas, hundreds or even thousands of light years across, created by the combined action of multiple massive stars in stellar associations. Dozens or hundreds of massive stars form nearly simultaneously in large molecular clouds. Their stellar winds and supernovae generate expanding shells of compressed gas surrounding a hot inner cavity. Superbubbles can break out of galactic disks into the halo, forming chimneys that vent hot gas and metals. High-velocity clouds, HVCs, are clouds of neutral hydrogen moving at speeds inconsistent with simple galactic rotation. Some may represent infalling gas accreted onto the galaxy, while others are material ejected from the disk and now falling back. Studying HVCs provides insight into the exchange of gas between galaxies and their surrounding environment. The Fermi bubbles are enormous gamma-ray structures extending thousands of light-years above and below the plane of the Milky Way. They were discovered by the Fermi Space Telescope. The origin of these bubbles is thought to be linked either to past activity of the central black hole or to a period of intense star formation in the galactic center a few million years ago. Similar structures have been observed in other galaxies as well. The supermassive black hole at the center of the Milky Way, Sagittarius A, has a mass of about 4 million solar masses. Its presence was confirmed by observations of stellar orbits near the galactic center. These stars move at tremendous speeds, reaching several percent of the speed of light along elongated elliptical orbits. The orbital periods of the closest stars are on the order of decades, allowing astronomers to observe complete orbits. An accretion disk forms around the black hole from infalling gas. Friction within the disk heats the gas to extremely high temperatures, causing it to emit radiation. The efficiency of converting mass into energy in an accretion disk can reach tens of percent, exceeding that of thermonuclear fusion. This makes accretion onto black holes one of the most powerful energy sources in the universe. Throughout the cosmos, relativistic jets, highly collimated streams of matter, are ejected from the vicinity of some active black holes at speeds close to the speed of light. The formation of these jets is linked to magnetic fields in the accretion disk and the rotation of the black hole. Jets can stretch across millions of light years, far beyond their host galaxies, creating giant radio lobes when interacting with the intergalactic medium. Radio galaxies are galaxies that emit powerful radio waves, often associated with jets from their central black holes. They are classified into two main types, Vanneroff-Rayleigh free and Vanneroff-Rayleigh II. Type I galaxies show radio brightness decreasing outward from the center, while Type II galaxies display bright hot spots at the ends of their radio lobes, where jets interact with the surrounding medium. This difference is related to jet power and environmental conditions. Quasars are the brightest and most energetic persistent objects in the universe. Their luminosity can exceed that of an entire galaxy by thousands of times, with most of the energy coming from a region comparable in size to the solar system. Quasars represent the active nuclei of distant galaxies, undergoing intense accretion onto supermassive black holes. They were more common in the early universe, indicating that black hole activity evolves over cosmic time. Seyfert galaxies are spiral galaxies with active nuclei. They are divided into two types based on the width of their emission lines. Type 1 Seyferts show both broad and narrow lines, while Type 2 Seyferts exhibit only narrow lines. The unified model suggests that this difference is due to the viewing angle. A thick, dusty torus surrounding the active nucleus can obscure the broad line region when observed edge-on. Blazars are active galaxies whose relativistic jet is directed almost exactly toward the observer. Because of relativistic effects, the jet's radiation is strongly amplified and appears highly variable. Blazars are powerful sources of gamma rays, and studying them provides insight into the physics of relativistic jets and the extreme environments near black holes. Variability in the activity of galactic nuclei over different timescales reflects changes in the accretion rate onto the black hole. Rapid variations occurring over hours or days indicate a compact emission region comparable in size to the black hole's event horizon. Slower changes may be linked to instabilities in the accretion disk or interactions with the surrounding medium. Feedback from active galactic nuclei, AGN, influences the entire galaxy. The released energy can heat or expel gas from central regions, suppressing star formation. This process may explain the observed correlation between the mass of the central black hole and the properties of its host galaxy. Without this feedback, simulations produce galaxies that are too massive, containing an excess of stars. Tidal disruption events, TDEs, occur when a star passes too close to a supermassive black hole. The tidal forces tear the star apart, and its remnants are accreted onto the black hole, producing a bright flare of radiation. These events make it possible to detect dormant black holes in galactic centers and to study accretion physics under extreme conditions. Intermediate mass black holes, IMPHs, with masses ranging from 100 to 100,000 solar masses, represent a missing link between stellar mass black holes and supermassive black holes. Their existence is theoretically predicted, but observational confirmation remains uncertain. Candidates for IMPHs have been found in the centers of some globular clusters and dwarf galaxies. The detection of gravitational waves from black hole mergers has opened a new window in observational astronomy. Gravitational wave detectors have recorded the merging of stellar mass black holes and neutron stars. Future detectors may be able to observe mergers of supermassive black holes in the centers of colliding galaxies, providing insights into the growth of black holes and the coevolution of galaxies. The evolution of galaxies and their central black holes is tightly connected. Galaxy mergers channel gas toward the center, feeding the central black hole and triggering active galactic nucleus, AGN, activity. Feedback from this activity can halt star formation. The correlation between black hole mass and galactic bulge mass suggests a fundamental link in their formation histories. The local group of galaxies includes the Milky Way, the Andromeda Galaxy, M31, and about 80 smaller galaxies. Its diameter is roughly 10 million light-years. Most members are dwarf galaxies orbiting the two largest spiral galaxies. Studying the local group provides detailed information about galactic processes that are impossible to observe in more distant systems. Gravitational interactions between the members of the local group strongly affect their evolution. The Andromeda Galaxy and the Milky Way are gravitationally bound and moving toward each other. Their collision is inevitable and will occur in a few billion years. Dwarf galaxies are gradually accreted by larger galaxies, adding stars and altering the structure of galactic halos. Tidal streams, long stretched-out structures of stars, form when dwarf galaxies or globular clusters are disrupted by the gravity of a larger galaxy. These streams encircle the galaxy, following the orbit of the disrupted satellite. Detecting and studying tidal streams helps reconstruct the accretion history and understand the distribution of dark matter in the galactic halo. The stellar halos of massive galaxies form from the remnants of accreted dwarf galaxies. Stars in the halo show diverse kinematics and chemical compositions, reflecting multiple origins. Studying the Milky Way, stellar halo, reveals its growth history through mergers with smaller systems over billions of years. Substructures within the halo, such as streams and stellar clusters, are remnants of disrupted satellites. Modern sky surveys are discovering more and more of these features, showing that accretion is still ongoing today. Some streams can be traced almost entirely around the galaxy, providing key information about its gravitational potential and mass distribution. Ultra-faint dwarf galaxies, whose luminosities are thousands of times lower than the Milky Way's, are the smallest known galaxies. They contain only a few thousand stars, yet are dominated by dark matter. These objects lie on the boundary between star clusters and galaxies. Discovering and studying them is vital for understanding the formation of the smallest dark matter halos. Dark matter does not interact with electromagnetic radiation, but its presence is revealed through its gravitational influence on visible matter. Galaxy rotation curves, the motions of galaxies within clusters, gravitational lensing, and the large-scale structure of the universe. All these observations require the presence of a significant amount of invisible matter. Dark matter makes up about 27% of the total energy content of the universe. Its nature remains unknown. Possible candidates include weakly interacting massive particles, WIMPs, axions, and other hypothetical particles beyond the standard model of particle physics. Despite numerous direct and indirect detection experiments, dark matter particles have not yet been observed. Their discovery would represent one of the greatest breakthroughs in physics. The distribution of dark matter in galaxies is studied using several methods. Rotation curves measure the gravitational potential at various distances from the galactic center. Gravitational lensing maps the distribution of total mass, including dark matter. The dynamics of stars and gas in galaxies also reflect the influence of dark matter. The results indicate the existence of extended dark matter halos surrounding the visible components of galaxies. The missing satellites problem refers to the discrepancy between the predicted number of small dark matter halos around galaxies and the observed number of dwarf satellites. Simulations predict hundreds or even thousands of subhalos, but only a few dozen dwarf galaxies have been observed. This may be explained either by special properties of dark matter or by baryonic processes that suppress star formation in small halos. Self-interacting dark matter, SIDM, is a model in which dark matter particles interact with each other, but not with ordinary matter. Such interactions may explain some discrepancies between simulations and observations, such as the shapes of inner density profiles of halos. Experiments and observations continue to constrain the possible properties of dark matter. The formation of structures in the universe begins with tiny initial density fluctuations. Regions with slightly higher density attract more matter, further increasing their density. This process of gravitational instability, first described in the 19th century, leads to the exponential growth of perturbations. Dark matter, which does not experience pressure, collapses first, forming halos that later attract baryonic matter. Baryons, heated as they fall into dark matter halos, must cool before stars can form. The efficiency of cooling depends on the mass of the halo and the metallicity of the gas. In small halos below a certain mass threshold, gas does not cool efficiently, and galaxies fail to form. This explains why not all dark matter halos contain visible galaxies. The epoch of reionization had a major impact on galaxy formation. Ionized gas was heated, increasing pressure and preventing collapse in small halos. This may have stopped star formation in the smallest halos, explaining the lack of observed dwarf galaxies within certain mass ranges. High-resolution cosmological simulations reproduce the formation of galaxies from initial conditions to the present day. These simulations track the evolution of billions of particles, representing both dark matter and baryons, taking into account gravity, hydrodynamics, and many other physical processes. The results are compared with observations to test and improve the models. Successful simulations reproduce many properties of galaxies, including their sizes, masses, star formation rates, and morphologies. However, some details remain challenging to model, requiring further refinement of subgrid physics. The parameters describing feedback from stars and black holes are often tuned to match observations, indicating an incomplete understanding of these processes. The interaction between observations and theory drives progress in galactic astrophysics. New observational data raise questions and constrain theoretical models, while theoretical predictions guide observers toward promising targets and phenomena. This cycle continues, constantly deepening our knowledge of galaxies and the universe. Future observatories promise to revolutionize the study of galaxies. The James Webb Space Telescope is already providing unprecedented images and spectra of distant galaxies. Ground-based telescopes with giant mirrors will make it possible to study the details of galaxies at great distances. Radio and gravitational wave astronomy will reveal new aspects of galaxies invisible in the optical range. The study of galaxies brings together a wide range of disciplines and methods, from observations across different parts of the spectrum to numerical modeling and theoretical analysis. Each approach contributes to the overall picture. Galaxies are the fundamental building blocks of the universe, and understanding their nature and evolution is critical for understanding the cosmos as a whole. Stellar populations within galaxies differ in age, chemical composition, and kinematic properties. These differences reflect the history of star formation and the evolution of galaxies over billions of years. Astronomers traditionally divide stellar populations into two main classes, although in reality the division is more complex and continuous. Population includes young metal-rich stars that move in nearly circular orbits within the plane of the galactic disk. These stars formed relatively recently from gas already enriched by the products of earlier generations of stellar evolution. The Sun belongs to this population. The ages of population 1 stars range from a few million years for the youngest to several billion years for the older ones. Population 2 consists of old, metal-poor stars moving in elongated orbits with large inclinations relative to the galactic plane. These stars formed during the early stages of galaxy formation, when the interstellar medium had not yet been significantly enriched with heavy elements. Population 2 stars occupy the halo and thick disk of galaxies. Their ages are close to the age of the galaxy itself, reaching up to 13 billion years. The metallicity of stars is measured by the relative abundance of iron and other heavy elements compared to hydrogen. Astronomers use a logarithmic scale where the Sun's metallicity is set to 0. Stars with metallicity 2 contain 100 times fewer heavy elements than the Sun. The most metal-poor stars show metallicities below 5, containing 100,000 times fewer heavy elements than the Sun. The study of extremely metal-poor stars provides information about the earliest generations of stars. Their chemical composition reflects the products of the first supernovae in the universe. The abundance patterns of various elements indicate the processes that occurred within these ancient stars. The detection and analysis of such stars help reconstruct the chemical evolution of the early universe. The thick disk of a galaxy represents an intermediate structure between the thin disk and the halo. Stars of the thick disk have metallicities lower than those in the thin disk, but higher than those in the halo. Their kinematics show a larger velocity dispersion, which leads to an increased vertical thickness of the stellar distribution. The origin of the thick disk is still debated. It may have formed through the heating of the thin disk during galactic mergers, through accretion of stars from disrupted satellites, or during early, intense star formation in the turbulent environment of a young galaxy. The chemical evolution of galaxies describes the changes in the chemical composition of the interstellar medium over time. Each generation of stars produces heavy elements and returns them to the interstellar medium through stellar winds and supernova explosions. The next generation of stars forms from this enriched gas. The rate of enrichment depends on the efficiency of star formation, the initial mass function, and the loss of gas from the galaxy. Different elements are produced in different astrophysical processes. Light elements up to iron are synthesized in the cores of massive stars and released during core collapse supernova explosions. Iron and nearby elements are efficiently produced in Type Ia thermonuclear supernovae, which occur when white dwarfs explode in binary systems. Elements heavier than iron are created through neutron capture processes that occur under various physical conditions. The rapid neutron capture process, R process, happens at extremely high neutron densities, such as those reached during neutron star mergers and possibly in certain types of supernovae. This process is responsible for forming the heaviest elements, including gold, platinum, and uranium. The gravitational wave event from a neutron star merger, detected in 2017, was accompanied by optical emission, the spectrum of which showed signatures of heavy element formation. The slow neutron capture process, S process, occurs in asymptotic giant branch AGB stars, which represent a late stage in the evolution of intermediate mass stars. This process produces about half of all elements heavier than iron. The S process operates under low neutron densities, allowing atomic nuclei to decay between neutron captures, resulting in the creation of stable isotopes. The relative abundances of different elements in stars of varying ages reveal the timescales of various enrichment processes. Massive stars evolve rapidly, enriching the interstellar medium with alpha elements such as oxygen, neon, magnesium, and silicon within tens of millions of years. Type Ia supernovae, however, occur later, since they require the evolution of binary star systems, adding iron with a delay of hundreds of millions or even billions of years. Stars that formed during the first few 100 million years of a galaxy's existence show enhanced alpha to iron ratios compared to younger stars. This indicates that early chemical evolution was dominated by the contribution of massive stars. As thermonuclear supernovae began contributing, the alpha to iron ratio gradually decreased. Stellar archaeology uses the chemical composition of old stars to reconstruct the history of a galaxy. Each star preserves the chemical signature of the gas cloud from which it formed in its atmosphere. Detailed spectral analysis allows astronomers to measure the abundances of dozens of elements. Stars with unusual abundance patterns can indicate specific processes or rare events in the past. Carbon-enhanced metal-poor CMMB stars show a high carbon content despite their overall low metallicity. Their origin is linked to mass transfer from a binary companion star that has passed through the asymptotic giant branch stage. Such stars provide insights into the frequency of binary systems and mass transfer processes in the early generations of stars. Stars with extreme elemental ratios may be enriched by the products of a single nearby supernova. If a star forms from gas polluted by only one or a few supernova, its chemical composition reflects the yields of those specific explosions. Studying such stars helps astronomers understand the processes within individual supernovae and their variations. Nucleocosmochronology uses radioactive isotopes with long half-lives to estimate stellar ages. Thorium and uranium, produced in the R process, decay over billions of years. By measuring their current abundances and knowing their initial ratios, scientists can estimate the time elapsed since the formation of these elements. This method is applied to the oldest metal-poor stars. The ages of star clusters are determined by comparing their observed color magnitude diagrams with theoretical stellar evolution models. The turn-off point, the location where stars begin to leave the main sequence, is directly related to the cluster SH. Older clusters have turn-off points at lower luminosities and redder colors, since more massive stars have already evolved off the main sequence. The oldest globular clusters in the Milky Way are about 13 billion years old, close to the age of the universe itself. Determining their precise ages is important for cosmology, since the universe cannot be younger than its oldest objects. Modern measurements show consistency between the ages of the oldest stars and the age of the universe, determined from cosmological observations. White dwarfs represent the final evolutionary stage of low and intermediate mass stars. After the exhaustion of nuclear fuel and the shedding of outer layers, a dense core remains, supported by the pressure of a degenerate electron gas. White dwarfs do not produce energy through thermonuclear reactions and gradually cool, radiating their stored heat. The cooling rate depends on the mass and composition of the white dwarf luminosity function. The distribution of white dwarfs by brightness shows a cutoff at low luminosities. This cutoff corresponds to the age of the galactic disk, since the coolest white dwarfs are remnants of the oldest low-mass stars. The position of this cutoff can be used to estimate the age of stellar populations. Neutron stars are formed during the collapse of massive stellar cores in supernova explosions. Matter compresses to densities comparable to those of atomic nuclei. The mass of a typical neutron star is about 1.5 solar masses, but its radius is only about 10 kilometers. This makes neutron stars some of the densest objects in the universe, second only to black holes. Pulsars are rapidly rotating neutron stars with powerful magnetic fields that emit narrow beams of radiation. If such a beam is directed toward Earth during rotation, we observe regular pulses of radiation similar to a lighthouse beacon. Pulsar rotation periods range from milliseconds to several seconds. Over time, pulsars slow down, losing rotational energy through radiation. Millisecond pulsars rotate hundreds of times per second. They form in binary systems, where accretion of matter from a companion star spins up the neutron star. Millisecond pulsars are used for precision timekeeping and for detecting gravitational waves through pulsar timing monitoring. A network of millisecond pulsars acts as a detector for very low-frequency gravitational waves. Magnetars are neutron stars with extraordinarily strong magnetic fields, 1,000 times stronger than those of ordinary pulsars. The decay of these magnetic fields heats the star and powers intense bursts of X-ray and gamma radiation. Magnetars exhibit irregular activity, sometimes producing giant flares visible from thousands of light years away. Stellar mass black holes form from the collapse of the most massive stars. If the collapsing core exceeds the stability limit of a neutron star, around 2 to 3 solar masses, the collapse continues until a black hole forms. Direct observation of black holes is impossible, but their presence is inferred through their gravitational influence on surrounding matter. X-ray binary systems contain either a black hole or a neutron star accreting material from a normal companion star. The infalling matter heats up to millions of degrees and emits brightly in the X-ray range. Measuring the mass of the compact object through binary dynamics allows astronomers to distinguish between neutron stars and black holes. Microquasars are X-ray binary systems with relativistic jets. They are miniature versions of active galactic nuclei and allow scientists to study accretion and jet physics on more accessible scales. The jets of microquasars sometimes exhibit apparent superluminal motion, a projection effect that occurs when they move close to the line of sight at relativistic speeds. Gravitational wave observatories detect mergers of black holes and neutron stars. The first direct detection of gravitational waves occurred in 2015, resulting from the merger of two black holes with masses of about 30 suns each. Since then, dozens of such events have been recorded, revealing the population of binary compact objects in the universe. The merger of neutron stars produces not only gravitational waves, but also electromagnetic radiation, a kilonova, optical and infrared emission, powered by the decay of radioactive elements formed during the merger. Observations of kilonovae confirmed that neutron star mergers are the primary source of heavy elements in the universe. The initial mass function, IMF, of stars describes the distribution of masses among newly formed stars. It determines how many stars of each mass are created. Most stars have masses significantly lower than the sun's, with the number of stars decreasing toward higher masses. The initial mass function is critically important for understanding stellar populations and chemical evolution, since massive stars make a disproportionately large contribution to enriching the interstellar medium despite their small numbers. Low-mass stars, red dwarfs with masses from 10 to 50% of the Sun, are the most numerous stars in the galaxy. They burn fuel extremely slowly, with lifetimes exceeding trillions of years. No red dwarf has yet completed its evolution, as the age of the universe is still too short. These stars make up a significant portion of the stellar mass of the galaxy, although they contribute relatively little to its total luminosity. Brown dwarfs form in a similar way to stars from collapsing gas clouds, but their masses are insufficient for sustained hydrogen fusion. Brown dwarfs have masses between about 13 Jupiter masses, the threshold for deuterium burning, and roughly 80 Jupiter masses required for hydrogen fusion. They represent the transitional class between stars and planets. Substellar objects with even lower masses than brown dwarfs are classified as planets or planetary mass objects, planemos, bodies not orbiting any star. The boundary between brown dwarfs and planets is defined both by the ability to burn deuterium and by the mechanism of formation. Objects formed through direct gravitational collapse of a gas cloud are considered brown dwarfs, while those formed in protoplanetary disks are classified as planets. Exoplanets have been discovered around thousands of stars, revealing an enormous diversity of planetary systems. Detection methods include transits, when a planet passes in front of a star and slightly dims its light, and radial velocity measurements, which detect the gravitational pull of a planet on its star. Direct imaging of planets is possible only for large young planets on wide orbits around nearby stars. Hot Jupiters, gas giants orbiting very close to their stars with periods of only a few days, were a surprising discovery, since formation models predicted gas giants should form far from their stars. Their existence is explained by planetary migration, a process that moves planets inward or outward from their formation sites through interactions with the gas disk or with other planets. Super-Earths and mini-Neptunes are planets with masses between Earth and Neptune, a category absent in our solar system. They are the most common type of exoplanet detected through the transit method. Their internal structures and atmospheric compositions vary widely, from rocky planets with thin atmospheres to worlds with thick hydrogen-helium envelopes. Planets located in the habitable zone, where temperatures allow liquid water to exist on the surface, are of special interest in the search for life. The habitable zone's distance depends on the luminosity of the star. For brighter stars, it lies farther out. Dozens of planets have been discovered in habitable zones, although most orbit red dwarfs, raising additional questions about the habitability of such systems. Red dwarfs have characteristics that strongly affect potential habitability. Their habitable zones lie very close to the star, where planets often become tidally locked, always showing one side to the star. Red dwarfs can also be highly active, producing powerful flares that irradiate nearby planets. However, their longevity and abundance make red dwarf systems key targets in the search for extraterrestrial life. The atmospheres of exoplanets are studied through transit and eclipse spectroscopy. When starlight passes through a planet-ES atmosphere during a transit, it carries molecular fingerprints revealing the atmospheric composition. Observations across different wavelengths allow scientists to identify water vapor, carbon dioxide, methane, and other atmospheric components. Future telescopes may be able to detect biosignatures, signs of biological activity, such as oxygen or methane, appearing together in specific combinations that would be difficult to explain without life. The formation of planetary systems takes place in protoplanetary disks, rotating disks of gas and dust surrounding young stars. Dust grains collide and stick together, forming increasingly larger bodies called planetesimals. These planetesimals then collide and merge, creating protoplanets. Gas giants form either by the accretion of gas onto a solid core or by the direct gravitational collapse of part of the disk. The snow line in a protoplanetary disk marks the distance from the star, where the temperature is low enough for water ice to condense. Beyond the snow line, there is a greater abundance of solid material due to the presence of ice, which promotes the formation of larger planets. This explains why the gas giants in our solar system are located beyond the snow line. Planetary migration within the disk occurs due to the gravitational interaction between a planet and the surrounding gas. The planet creates density waves in the disk, which exchange angular momentum between the planet and the gas. Depending on conditions, the planet can migrate inward or outward. Rapid inward migration of massive planets may lead to their falling into the star if the process is not halted. The late heavy bombardment in the solar system, a period of intense impacts by large bodies on the inner planets about 4 billion years ago, may have been triggered by orbital rearrangements among the outer planets, which sent numerous small bodies into the inner solar system. The delivery of water and organic compounds during this time could have played a role in the emergence of life on Earth. The formation of the Moon is explained by a giant impact between the early Earth and a Mars-sized planetesimal about 4.5 billion years ago. The ejected debris formed a disk around Earth, from which the Moon rapidly accreted, Simulations show that such giant collisions were common during the late stages of planetary system formation. Multi-planet systems display a wide variety of architectures. Some contain several planets on close, nearly coplanar orbits, while others have planets with highly inclined or eccentric orbits. Orbital resonances between planets can stabilize certain configurations. The TRAPPIST-1 system contains 7 Earth-sized planets, 3 of which lie within the habitable zone. Multiple star systems are common. Roughly half of Sun-like stars have one or more stellar companions. Planets have been found in binary systems, either orbiting one star or both stars on wide circumbinary orbits. Circumbinary planets experience a complex gravitational environment and may have unusual patterns of illumination. Free-floating planets, planets not bound to any star, drift through the galaxy independently. They may have been ejected from planetary systems through gravitational interactions. Estimates suggest that such rogue planets could be as numerous as, or even more numerous than, the stars in the galaxy. Detecting them is challenging because they emit little to no light, but it is possible through gravitational microlensing. Gravitational microlensing occurs when an object passes in front of a distant star, and its gravitational field bends and focuses the star's light, temporarily increasing its brightness. The duration and shape of the light curve depend on the mass of the lensing object. This method is sensitive to planets on wide orbits and to free-floating planets. Finally, astrobiology explores the possibility of life beyond Earth, seeking to understand where and how life might arise elsewhere in the universe. When he was killed in 336 BCE, he had been preparing for a grand expedition to subdue Persia. He already possessed all the means necessary for conquest, which he passed on to his son Alexander. The pharaohs of the 30th dynasty upheld the honor of Egyptian royal authority and left behind impressive monuments, following the example of their predecessors. Thus, although the late period can be considered the end of Egyptian sovereignty, it should not be regarded as the end of Egyptian civilization. Even today, Egypt's cultural achievements command respect, if not awe, and remain among the most popular and intriguing in the ancient world. Though times have changed, modern Egypt of the 21st century may be seen as an evolved version of ancient Egypt. The Nile River is still sacred to the Egyptian people, who continue to celebrate many of the same ancient festivals, such as the spring celebrations. The cuisine is still largely inspired by authentic ancient dishes. Traditions remain alive. Even the final stage of the ancient language, Coptic, is still used in Egypt during church services and can be heard in their Arabic dialect. The modern inhabitants take great pride in their heritage. This was evident during the parades in Cairo, dedicated to the transfer of royal mummies to the Museum of Civilization and the reopening of the Avenue of Sphinxes in Luxor. They are building new cities and cutting roads through mountains and deserts to improve trade. The world's largest museum is soon to open. Daily excavations continue to bring new discoveries that may one day rival the finding of Tutankhamun's tomb in 1922. And this land will forever remain a captivating enigma, dazzling and enchanting people from all over the world with its magic and history. Life on Earth emerged relatively quickly after the planet's formation, which may indicate that the origin of life is a natural process under suitable conditions. The key requirements include liquid water, an energy source, and organic molecules. However, the range of conditions under which life can exist remains uncertain. Extremophiles on Earth, organisms that live in extreme environments, such as high temperature, acidity, salinity, or radiation, expand our understanding of the potential habitability of other worlds. The discovery of life in extreme environments on Earth increases optimism about the possibility of life on planets and moons that were once thought to be uninhabitable. The moons of the giant planets in the solar system are of great interest to astrobiology. Europa, a moon of Jupiter, has a subsurface ocean of liquid water beneath its icy crust. Enceladus, a moon of Saturn, ejects geysers of water vapor and organic molecules from a subsurface ocean. These moons may have conditions suitable for life, despite being far beyond the traditional habitable zone. The search for extraterrestrial intelligence uses radio telescopes to listen for possible signals from technologically advanced civilizations. These programs scan the sky at various frequencies, searching for narrowband signals or other signs of artificial origin. So far, no convincing signals have been detected, but the search continues with improved sensitivity and coverage. The Fermi paradox poses the question: if intelligent life is common in the universe, then where is everyone? Various explanations include the rarity of intelligent life, the self-destruction of civilizations, a lack of interest in contact or interstellar travel, or technological limitations on communication. Resolving this paradox has profound implications for the future of humanity and our place in the universe. The Drake equation estimates the number of communicating civilizations in the galaxy by multiplying factors such as the rate of star formation, the fraction of stars with planets, the number of planets in the habitable zone, the fraction of planets that develop life, the fraction of life that evolves intelligence, the fraction of civilizations that produced detectable signals, and the duration of such civilizations. Most of these factors are poorly known, making the estimate highly uncertain. Technosignatures are indicators of technological activity that could be detected across interstellar distances. They include radio transmissions, laser pulses, changes in planetary atmospheres due to industrial activity, or megastructures such as Dyson spheres surrounding stars to collect energy. The search for technosignatures complements the search for biosignatures and may detect civilizations more advanced than our own. Interstellar travel remains technologically challenging due to the immense distances involved. The nearest stellar system, Alpha Centauri, is 4.25 light-years away. With current technology, a journey there would take tens of thousands of years. Proposed concepts such as solar sails or fusion engines could reduce travel time to decades or centuries. Panspermia is the hypothesis that life can spread between planets or even star systems via meteorites or other mechanisms. Microorganisms can survive in space in a dormant state and revive upon reaching a suitable planet. The exchange of material between planets within the same system is quite possible, but interstellar panspermia would require survival for millions of years in interstellar space. The origin of life on Earth remains an unresolved question. Early Earth's conditions included an atmosphere different from the modern one, oceans, volcanic activity, and intense meteorite bombardment. Experiments have shown that organic molecules, including amino acids, can form under the conditions of early Earth. The transition from simple organic molecules to self-replicating systems is a key step, the mechanism of which is actively studied in the RNA world hypothesis. This hypothesis suggests that early forms of life used RNA, both as genetic material and as a catalyst for chemical reactions. RNA can perform both functions, unlike DNA and proteins, which are specialized. The discovery of ribozymes, RNA molecules with catalytic activity, supports this hypothesis. The transition from RNA to DNA and proteins occurred later, providing greater stability and efficiency. Hydrothermal vents on the ocean floor create chemical gradients and sources of energy that could have promoted the origin of life. Warm, mineral-rich water emerging from cracks in the oceanic crust creates conditions for chemical reactions that produce organic molecules. Modern ecosystems around hydrothermal vents do not depend on photosynthesis. They derive energy from chemical reactions, demonstrating an alternative foundation for life. Photosynthesis revolutionized life on Earth by allowing organisms to use sunlight to synthesize organic compounds from carbon dioxide and water. Oxygenic photosynthesis, which produces oxygen as a byproduct, first appeared in cyanobacteria about 2.5 billion years ago. The accumulation of oxygen in the atmosphere led to the Great Oxygenation Event, which radically changed Earth's chemistry and paved the way for complex multicellular life. The Cambrian explosion, around 540 million years ago, was characterized by a rapid diversification of multicellular organisms. Most modern animal groups appeared within a relatively short geological period. The causes of this explosion are debated and may include reaching critical oxygen levels, the evolution of new genetic mechanisms, or ecological changes. Mass extinctions occurred several times in Earth's history, when a significant portion of species disappeared over geologically short periods. The largest extinction at the end of the Permian period wiped out over 90% of marine species. The extinction at the end of the Cretaceous period, which killed the dinosaurs, was caused by an asteroid impact. These events drastically altered the course of evolution, opening ecological niches for new groups of organisms. The evolution of intelligence and consciousness is of particular interest. Intelligence evolved independently in several lineages: primates, cetaceans, corvid birds, and cephalopods. This suggests that under suitable conditions, evolution can convergently produce cognitive abilities. However, the human level of intelligence, with language, culture, and technology, emerged only once on Earth, raising questions about its inevitability. The future of life on Earth is limited by the evolution of the Sun. In about 1 billion years, increasing solar luminosity will make Earth too hot for liquid water. Photosynthesis will become impossible, leading to the extinction of plants and the organisms that depend on them. In about 5 billion years, the Sun will expand into a red giant, possibly engulfing Earth. Long before that, humanity will have to find a new home if it wishes to survive.